and I'll invite Glen to start sharing his presentation.
Sure. Let me see if it's working. Do you see the presentation?
Yes, we can see the presentation.
Okay, very good. And the pointer as well.
Yes.
Okay. Okay. Thank you very much for the nice introduction and for the opportunity to talk about the latest work that we have been doing here in Innsbruck. So as you would expect, the main topic of this work is quantum annealing, or in general, this is in general a procedure to solve classical optimization problems, and by first encoding the problems into a target Hamiltonian and mapping the classical problem to the problem of finding the ground state of the classical Hamiltonian. Then to the new quantum Hamiltonian is supplemented with a driving Hamiltonian, and this is used to generate a Schrödinger dynamic by considering the annealing Hamiltonian, which is obtained interpolating the two Hamiltonian. So this is a time-dependent interpolation. So it's an evolution with a time-dependent Hamiltonian. Nevertheless, we can not compute this evolution exactly, but having a device, we can initialize the system in a particular state, for example, the ground state of the driving Hamiltonian. Let the Hamiltonian evolve under this interpolating Hamiltonian and read out the final state. So the goal would be to have a final state which is close enough to the ground state of the system, so that with enough measurements we can recover the sought classical state. And what is hard here, it's probably that I've not specified the shape of this annealing schedules, A of t and B of t, that are used for the interpolation. Here, A will be in general the coefficient multiplying the target Hamiltonian, the classical one, and B the driving, which is introduced quantum fluctuation. So one way to choose these coefficients, A and B, is relying on the Diabatic criterion. So according to the Diabatic criterion, if we choose the Hamiltonian, the coefficient in such a way that the initial Hamiltonian is the driving Hamiltonian, the final Hamiltonian is the target Hamiltonian, we can evolve the system, and the system will evolve. If the system is evolved sufficiently slowly, then it will end up in the ground state of the final Hamiltonian with high probability. And there is indeed an Adiabatic criterion that says that the speed at which the Hamiltonian is changing should be a lot less than the gap square. And this essentially says that when we encounter vanishing gaps, the algorithm to return a good solution has to requires long time. So this long time can be a problem in different scenarios. First of all, when implementing the algorithm on a quantum device, coherence times of the quantum device limit the times which are accessible at which we can do a coherent quantum evolution. Moreover, it may be that by these long times, due to the vanishing gap, make such a way that we cannot achieve a quantum advantage. Alias, we could find eventually classical algorithms which perform better because and require less time to find the solution. So one possible solution, let's say, to this problem of long time is optimizing the schedules A of t and B of t. So as I said, the adiabatic condition doesn't say much about the particular shape of the schedule, but Roland and Cerf, for example, show that it's possible to further optimize the schedule, imposing adiabatic condition locally, for example, but there are other techniques in such a way that the final result is obtained in a shorter time. And this is a great advantage for the reason we mentioned before. In this talk, I'll focus on the same approach, alias this schedule optimization. I'm trying to find schedules which are better than what one would a priori try. And to do this, I'll rely on a method called counterdiabatic driving. So let me start by introducing the counterdiabatic driving. So to do this, let's make a step backwards and let's consider the Hamiltonian in the lab frame. Here I call the annealing Hamiltonian H0 because it is the procedure is quite general and it's not restricted to quantum annealing dynamics. In the lab frame, the Hamiltonian, the state evolves according to the Hamiltonian, as we said. However, we may consider going to a moving frame in which, in the Diabatic moving frame, in which the Hamiltonian is diagonal. In this case, the Schrödinger equation for the states in this frame changes, and due to the fact that the transformation is independent, we get an additional term in the Schrödinger equation other than the standard rotated Hamiltonian. So, since the rotated Hamiltonian is diagonal in this moving frame, it will not generate transition between the eigenstates, in particular also between the ground state and excited states. So the only object that can generate transition in a diabatic condition in this frame, it's this object that has been here shown in green. So this object here is manifest, and it will be great to eliminate it because it's what is leading to low fidelities and low performance of the algorithm in the end. So indeed, the suggestion would be to consider counterdiabatic driving. This has been introduced already in 2003 by Rice and rediscovered by Baer in 2009. And in this approach, the Hamiltonian is modified. The HD Hamiltonian, so the Hamiltonian that we use to drive our system, is changed in such a way that we add to it exactly the term which would cancel out this green term. So this term that I write here is if one does the math, we'll find that exactly, but after inserting it again in the moving frame, all what is left is the adiabatic, is the diagonal part of the Hamiltonian. So when this Hamiltonian HCD is used with this gauge potential given here, there are no additional transitions, and this realizes the perfect dynamic. So which gives the ground state. So then it would seem that we have solved the problem, but it's not exactly like this, because to obtain this gauge potential, which is named A, we need full spectral information. So we need actually to know the eigenstates and eigenvalues of the Hamiltonian, in our case, the annealing Hamiltonian at each time t. And this is actually harder than just getting to know the eigenstates at the final time, and which is our goal. And moreover, we have a problem, and that is that this expression for A, which is exact, introduces non-local interaction. So we have a proliferation of interaction terms, which may be also non-local and may be quite hard to realize in an experiment. So in this case, a great step forward in this direction into applying these counterdiabatic driving techniques to many body systems, and in particular to quantum annealing, was achieved by Sells and Polkovnikov in 2017, where they show that the the distance between an arbitrary operator A and the exact gauge potential can be up to a constant, which is fixed, can be quantified by the trace of the squares of this operator that we write here on the right. So this operator contains the derivatives of the Hamiltonian, H0, and a commutator with this operator. So here we see that we can recast the problem of finding the exact adiabatic gauge potential, which is needed to find the counterdiabatic driving, into the problem of minimizing this action F. So once we have done this, it would seem that the problem is much more simple because we do not have to diagonalize the Hamiltonian. And in particular, conveniently, we can also consider variational ansatz, which depends on variational parameters, which we can use to approximate the exact adiabatic potential. And this approximation can be obtained by minimizing the action, that is the distance from the exact adiabatic potential, with respect to the variational parameter. So this approach, as I mentioned, has been applied to quantum annealing, like with, let's say, in some cases with success. But here I just want to point to these two works, one from Hartmann and Lechner, and one from Passarelli and co-workers. In the first one, they show essentially that this approach, when applied to certain architectures, can give an advantage. And in the second one, they extend the approach to consider noise and to consider open systems, which is quite important because in actual devices, the systems are open. However, there are some problems with some problems can arise when considering this kind of approach. So here we consider, for example, following this recent paper still from the Innsbruck group, we consider a fully connected model where the spins are interact with random couplings. But the couplings are chosen between -1 and 1, but this is not quite important for the results we show. So we first consider an approximation of the adiabatic gauge potential, which is the standard one considered, which involves only local terms. So here we would actually allow all the local terms, so local fields in the adiabatic gauge potential. However, due to properties of the Hamiltonian, in particular, the Hamiltonian is real and contains no imaginary terms. Only the sigma y term contributes to the adiabatic gauge potential. And after optimizing the function, one can then compute, can apply it to a problem and compute the fidelity. So here for a problem for a time tau of 1, we see what happens when we first do the simple quantum annealing procedure. And in this case, we have that the fidelity decays and with the system size as to be expected. And when we apply this counterdiabatic driving with the approximate gauge potential with local spins, we find a slight advantage, but this is not, it doesn't show, it's not an advantage in scaling. So all we find in this case is an offset in the curves in the log plot. And to get an advantage in scaling, we find that in particular, it's necessary to consider further terms in the gauge potential. So one can, for example, generalize the ansatz and consider also terms with two spins. And this indeed gives an advantage, gives a better result in the performance of the algorithm. And it will seem that it also gives a better scaling of the final fidelity with respect to the size of the system. So we have not actually solved the problem because we are back to step one, because the potential here that we are having is hard to implement, and it contains interaction between y, x, or y, z on different sides on all of the system. Let me just mention that in theory, by going to higher order again, one can achieve also, as we said, fidelity 1, but this would continue to increase the complexity of the Hamiltonian that one has to implement. So to try to simplify the Hamiltonian, we considered this approach, and one can consider a physical frame rotation. So a physical frame rotation, here we denote it by R. Essentially, we rotate we want to see what is the dynamics in a rotated frame, which is not the lap frame. So if we consider a rotated frame, what happens is that the Hamiltonian which drives the system, so the effective Hamiltonian which describes the dynamics in the rotated frame, also changes. Here we call HRA this Hamiltonian, and similarly to what happened when we were doing moving frames in some slides before, we have a term which is simply the rotation of the counterdiabatic driving, which would want to rotate, plus a term that is due to the fact that this rotation is time dependent. However, if we are able to find for any rotation such that at time 0 and at final time gives the identity, we have that the state that the Hamiltonian HRA also prepares the ground state we were trying to prepare, because indeed we have that we are starting from an initial state phi tilde of 0, which is also equal to phi naught, because initially the two frames coincide, and we end up in the final state, which is phi of tau, which is also equal to phi tilde of tau, which is also equal to the third ground state, because the final frames coincide. And this would happen actually as long as we can maintain this boundary condition. So we have a problem because we are not trying to modify the Hamiltonian in such a way to make it simple. So Hamiltonian HRA is another Hamiltonian which produces the advantage of counterdiabatic driving, but it's different. I would want to choose R at this rotation in such a way that this new Hamiltonian we get can be implemented. So this approach has been considered in the literature by quite a few authors. And indeed, they have successfully found this R term for a particular system. So one qubit systems, or system which has some particular scale invariance, or some particular property, which greatly simplifies the problem. However, quantum annealing in general doesn't have this kind of greatly simplifying properties, and it will be convenient to have a technique that can find this R of t in a systematic way. So we consider this physical frame rotation, and we use them to introduce a rotated answer. So as we see, this is for now we make let's say a formal prescription would be to just see what will be the gauge potential associated with this Hamiltonian. So if we take, as we said, the gauge potential could be obtained by making the difference between the two Hamiltonians, HV and H0, and when we do that, we get that the final result for the gauge potential is written here, and this is quite a convenient result, because if we choose, I will not go into detail while these choices are convenient, but The problem is that this gauge potential simultaneously depends also on the derivative of time, and this makes it hard to optimize, or to minimize. So we need to make in such a way that to make this derivative of time to disappear, and we do this by reparameterization. So we introduce this auxiliary operator k, which is defined as such, and we also introduce a generator for the rotations, which we assume to be abelian. This actually is not a necessary condition to proceed, but greatly simplifies the problem. And if we do so, we can write both the supposed driving Hamiltonian HRA and the gauge potential in terms of these two auxiliary potential we have introduced, K and Q. And we see that in particular, the RA Hamiltonian has the advantage that now it only depends on K and Q dot. So if K and Q are chosen with allowed within the set of allowed operators, so will be the driving. And let's say that this also gives us the corresponding gauge potential, and this is which also depends on K and Q through R. And we can apply the same approach, variational approach, which was introduced by Polkovnikov, to now minimize this gauge potential A, to minimize the action with respect to the variational parameters in this gauge potential. And when this is done, this will return an HRA, which implements a better dynamics compared to the initial H0, which achieves better fidelity. So we tried this for start by trying it for a system of 2 spins. Okay, so this particular system, which is written here, and the couplings are chosen in such a way that the 2-spin system can be reduced to 2-level problem. And we use couplings which actually implicitly depend on this ramp. So the only effect that we actually require is that the couplings are smooth at the end and smooth at the beginning. So start with derivatives, which is null for all of these couplings. And this is a condition, as we said, that ensures that the boundary condition I described before for that the moving frame should be the same at the beginning and the end should hold. So it's a technical condition, but if needed. So let's go. First of all, in the approach I described, we have to find the parameters beta and gamma, which are used to let's say on which the potential A depends. So in this case, we know also exact solutions for the problem because, as we said, it reduces to a 2-level system and the exact solution can be computed. And we compare the results we obtain by numerical optimization of the cost function with the results obtained with the exact results. And we find that the results match. And this is quite good because in harder problems, the exact results are not going to be available, and we are going to have to resort to some computation to compute them. And here on the right, I show the fidelities, and as you can see, from starting from the unassisted driving A, which is here in the beginning, we have this drop, but the assisted driving gives a better fidelity, which is here in dark blue. And in particular, in RA in the light blue, I show the fidelity in the rotated frame, which does not show this drop because in the rotated frame, the system always follows the ground state as we have suppressed diabatic transition. But in the lab, we will see a drop due to the fact that the frames are not the same intermediate time. So let me just move, and I want to, in the few minutes that we have left, I just want to discuss the application of this approach to more complicated systems which arise in quantum annealing. So here we consider the same all-to-all model which we considered before, and we have the couplings, the couplings A of t and B of t, which depend on time. So we start our machinery, okay? We define our zero potential, we do all the optimization. This time we have no exact result. So these new functions that we see are obtained numerically and can be actually obtained efficiently with the local optimization, with the potential optimization algorithm, and produce the results that are given by the blue curve. So we actually find a fidelity improvement. And when we go and look for different system size, how this scales, we see that the red dots, which correspond to the local CD approach, which is the other one that can be implemented, still, as we shown before, do not show any scaling advantage over the baseline, which is the unassisted approach. While the new approach shows not only an improvement, but also an improvement that seems to scale with the system size. Let me just mention that this improvement is just the ratio between the fidelity of the driving we are considering and the unassisted driving. So it will be 1 for the unassisted driving. So just want to mention that here in Innsbruck we are quite familiar with encoding for annealing architectures, and we consider usually the problem of mapping non-local problems to local problems, so that they can implement it in a device. And this is done with we consider this here in Innsbruck done with the parity encoding, where the links where the configuration or the respective configuration to spin as E as J is encoded in a single physical spin. However, to maintain, since the space is increased, we have to introduce constraints which allow the system to, which allow the two ground states of the two Hamiltonians to coincide. So we can minimize the Hamiltonian of the LZ instead of minimizing the original Hamiltonian. And this is this provides a local Hamiltonian in 2D, which is can be implemented more easily. So we tried our approach also on the LZ Hamiltonian. Here we find an example for 6 spins. We have these constraint terms, which are the square, which are introduced a higher interaction between 3 and 4 spin in this case. And again, in this case, we have an additional Hamiltonian, which is the one that sets the constraint. And we can, then we have 3 parameters that we can change. So we perform, again, the same machinery with the rotated ansatz. And what we do in this case is add this additional parameter, which is within the theory acceptable. We just need to change slightly the answer. And finally, we find that this also, again, produces an improvement also for the LZ architecture, which is for this other parity encoding. And here I show a single size, the one shown in the figure of 6, and we see that the dynamic again shows a little dip for the RA protocol, which says that it's not exactly adiabatic, but in the end it gives a better fidelity. And the scaling advantage is still retained also in this other architecture. So this is quite positive. So I'll just conclude by saying that we explored counterdiabatic driving to find new schedules for quantum annealing, and this is quite proficuous. We found it to give an advantage also for different annealing architecture. So this is they can be actually different new directions that we can look for. In particular, we could try to consider complex and abelian transformations that were used to further improve the fidelity, because we did this. We consider this assumption to simplify the problem. We could add noise with techniques similar to those introduced by Pastorelli, and see whether how the shape of the schedule changes with noise. And we could also reiterate the algorithm. So try to take the result of one or eight iterations of these protocols that we see on the right and use them as new starting protocols. So we want to see if we could try to see if the algorithm can further improve against the new protocols, given, let's say, after a second iteration, producing a higher fidelity. So thank you for your attention.
Thank you very much, Glen, for your nice talk on behalf of the audience here. Now I will open the floor for questions. So anyone who wants to give a question to Glen, please unmute yourself. Perhaps I can start with a question. So in this rotating frame method, so you have to find the optimal coefficients, right, to get this better fidelity. Yeah. How do you think this scales when you increase the number of qubits? Is it going to be harder to find these optimal coefficients? Do you have any?
Yes, just give me, yes. So yes, so I consider mainly these two problems, and we show that for these two problems, at least the action can be computed exactly, in particular in the usual quantum annealing quadratic architecture, let's say on the usual all-to-all model, computing the action costs n squared, where n is the number of qubits. And similar results hold also for the parity architecture. So at least the computation of the action is quite fast. While so then that's a good point, because if we want to optimize an object, it's good that we can compute it quickly. So regarding the difficulty of optimizing, so here as we show here, the advantage is that each point we find it's quite close to the previous point, and actually it's a condition we can also require, because we will need to compute derivative of this function. So we need these functions to be quite regular. So since if the functions are regular, we can, and we know the initial point in particular, we can use an algorithm which for the successive use the previous point as initial guess to search for the next point. And we found that such an algorithm, the number of iterations required to solve the problem, we didn't find it to scale. We find it to scale just polynomially with the system size as well. So the advantage is that we can do this by doing it locally, and we only have two parameters. I want to recall that there are only two parameters to optimize at each point, and so there is not an increase of the parameters, and the cost function is very easy to compute. So these three ingredients together makes us the way that the optimization is actually not a problem. So finding the scale is not a problem. Particularly for translational invariant systems, we can also often find the schedules directly in the thermodynamic limit.
I see. Okay, thank you. Thank you for the answer. Are there any other questions from the audience? Well, I see no questions. I'll ask one more as an experimentalist. What do you think the challenges are for an experiment to implement this idea? Have you considered that?
So I don't see immediate challenges in implementing the driving. As I said, the driving is one has to just modify the scheduled functions. For example, the D-wave machine, for example, also allows this already. Just that the main question will be whether one can exactly produce this new scheduled function, and whether or what is the degree of change allowed in the scheduled function. For example, in the wave, one can at the moment choose only 11 points for the interpolation, but that would simply mean that from the theoretical point of view, we have to again do the computation, which is with 11 points instead of the many points that we use in this case. And this would actually make things easier. However, we would have to verify whether this improvement is maintained also when we are using such approximate functions.
I see. So it's like the discretization of these functions that may impose a limit on the fidelity you can achieve.
Yes, the discretization of this function will definitely impose a limit on the fidelity we can achieve. But the hope is that anyway, the fidelity could improve with respect to the naive quantum annealing.
Okay, well, that would be interesting to see implemented. Very good. Any last minute question? If not, I will thank Glen again and everybody else for attending. And I'll look forward to seeing you all in the next INQA seminar in 2 weeks. Bye now from anywhere you're joining us.
Okay, thank you again for your time.